Hi everyone, my name is Marco Agudo. My team members are Lauren Knapp and Sabrina Shen, and we are ME Team 34. Our project is the expulsion of a cylindrical body from an outer tube by explodable volumes. Our industry sponsor is Dr. James LeBlanc from Newark, and our faculty advisor is Professor Tien Feng Liu.
Newark, or the Naval Undersea Warfare Center, is located in Newport, Rhode Island. Engineers at the center research, develop, test, and evaluate the technologies utilized by the U.S. Navy's underwater warfare systems.
The purpose of our project is to design and build a working proof of concept that can vertically launch a cylindrical object from an underwater launch tube using an explosive volume, such as an expanding gas, to create an impulse force. Our project deliverables include our research of implodable and explodable volumes, CAD models of our designs, the calculated exit velocity and impulse force, and a working prototype. Our design requirements include a 1:8 ratio between the outer diameter and length of the launch tube. The diameter of the launch tube can be no more than 3 inches. The system must be launched in a vertical orientation, and one end should be open to the environment while one is closed. The cylindrical object needs to be negatively or neutrally buoyant, and the system must operate underwater without an external power source.
We researched different methods of explosion and explored their viability. Explosion with carbon dioxide gas cartridges was chosen to be the final design because the pressurized gas from CO2 cartridges can be easily controlled and quickly released in a matter of seconds. The cylindrical body starts from rest and accelerates upward in the axial direction of the launch tube as carbon dioxide is injected into the tube. When the cylindrical object is in motion, there are 5 forces acting on the object as shown in the free body diagram to the right. In order to keep the object moving, the force of CO2 must be greater than the other 4 forces as shown in the equation in the red box. We applied ideal gas law, conservation momentum, and impulse force equation to calculate the theoretical exit velocity of the cylindrical body and the impulse force needed to deploy the body as a function of launch tube height. The relationships between the velocity, impulse force, and the height were determined and plotted as displayed on the right. When the tube is 2 foot long, the cylindrical body has an exit velocity of 5.28 feet per second and experiences an impulse force of 0.45 pound per second. We're going to validate these values with experimental results in a later slide.
Our prototype has 3 main components: a pressure regulator, squared in green, the launch tube, and the cylindrical body. On the input side of the regulator is a bike tire inflator for connecting the CO2 cartridge, circled in red, and on the output side, a rubber hose connects the regulator to the bottom of the launch tube. The launch tube is constructed from a pipe size 3 PVC tube and pipe fittings. The cylindrical body is milled from aluminum 6061 and is hollowed out for a foam insert. Our test rig consists of a test stand to mount our prototype and a homemade testing tank for underwater experimentation. Both assemblies are of simple construction. Our test stand is made of plywood, hose clamps, and pocket screws, and our tank is made of 5 panels of plywood constructed with brackets, metal strapping, wood glue, as well as 2 layers of waterproof tarpaulin plastic that line the inside of the tank.
During testing, the test stand was clamped onto one side of the tank, and the prototype without foam insert was tested 3 times. Each trial, 120 psi of carbon dioxide gas was delivered to the launch tube, and a slow motion camera was used to capture the cylindrical body's travel time. As shown in the video, the cylindrical body was able to fully depart the tube in under half a second, so we can conclude that the objective of this project was successfully met. The average experimental exit velocity was determined to be 4.93 feet per second and produced a 6.71% error when compared to the theoretical result. The average experimental impulse force was 0.34 pound per second, with an error of 24.06%. Inaccurate time measurement was the major source of error. It was difficult to tell when exactly the cylindrical body started moving in the solid launch tube. Therefore, a better testing site or timing system should be considered in the future to improve the results. Overall, we have confidence in these experimental results and believe that they can be used to validate the theoretical calculations discussed earlier.
We successfully met all of our sponsors' requirements. For future experimental testing, we recommend utilizing Yukon Avery Point's water tanks. We also recommend running the experiments using inductive proximity sensors in a data acquisition system. As seen in the image on the right, the sensors will be placed at the bottom and top of the launch tube and record the time it takes for the cylindrical object to travel the length of the tube. This will give more accurate test results when calculating the exit velocity and impulse force. Additionally, tests should be conducted utilizing various foam types and carbon dioxide pressures to see how the exit velocity and impulse force changes with different combinations.
Although we're disappointed in not being able to continue improving our prototype, we still appreciated the senior design experience. We'd like to say special thanks to everyone who guided and helped us with our project. Thank you for watching our presentation.